Right.
This meeting is being recorded.
Okay, thank you, Dr. Uma. So a very warm welcome to everybody around here. Since we come from very different continents, so it's probably morning on your country, it's late evening in mine, and it's probably night in some. So we are here today together to have academic disclosure for quantum communication. So welcome to International Quantum Communication Seminar 2023. I myself, Dr. P.Yukthamarani Permarupan. I'm from University Malaysia, Kelantan. I'm currently a senior lecturer with the School of Malaysian Graduate School of Entrepreneurship and Business. Today we have 6 prominent speakers from different fields that will be joining us. I would like to introduce Dr. Zulkarnaen, Dr. Subhash Bansal, Dr. Kumar Gautam, Ms. Tanya Sharma, Mr. Arka Mukherjee, and Mr. Santanu Ganguly. This will be your distinguished speakers today. Without further ado, I'm going to call upon the first speaker, which I have with me today, which will be Associate Professor Dr. Zulkarnaen. He's from University Malaysia, Kelantan. He's a founder of Creative Lab UMK. He has been involved in the ICT degree industry and academic for the past 20 years. He has graduated in computer science degree and diploma, majoring in software engineering. He has a master's degree specialized in information privacy and ICT strategic planning. He is also a certified master trainer for computer thinking, recognized by the Malaysian government and also Malaysian Digital Economic Corporation. He has obtained several formal and informal entrepreneurship qualifications, such as professional certificate in entrepreneurial leaders from Swansea University, UK. He is also one of the MDEC certified computer training master, and is also recognized as one of the most outstanding entrepreneurship mentor Malaysia in 2018. He has received various recognition and awards in research and innovation competition at national and international level. Without further ado, Dr. Zulkarnaen, are you there? I saw him just now.
I know he is available.
Yeah.
Maybe there's something.
I saw him just now. Yeah, 1 second.
Dr. Nick.
Dr. Nick.
One second. Dr. Nick. Okay. Or can we move to the another person, Doctor?
Sure. Do I have Dr. Kumar?
Dr. Kumar, can we start with you?
Yeah, sure. No problem.
Are you there, Dr. Kumar? Okay, it's a great pleasure, Dr. Kumar.
Okay.
I'll just give you a short introduction of yourself before I pass the floor to you. So Dr. Kumar Gautam is a founder and president of Quantum Research and Center of Excellency, which is known as QRACE, as well as eGreen Quanta. QRACE is an independent incubator center with a decentralized community of researchers and scientists with noble ideas and global mindset, working together to change the world. Societal applications are developed. He is an associate professor and has demonstrated history of working with higher education industry and a proficient in MATLAB, quantum computation, Python, algorithm, and research. He also has a strong educational professional with a PhD from Delhi University focused on quantum gate design based on Schrodinger dynamics. His mission model is focused on quantum gates based on excitation of atoms and molecules with electromagnetic fields, making it a laser field interaction with trapped on. So without further ado, I think you will be starting off with the main topic of the day, which is quantum communication. So the floor is all yours, Dr. Kumar.
Yeah. Okay.
Others, please mute yourself.
Kumar, you can mute those persons.
Sa gustong mahinuman o seafarer, ay nagkaroon sa Negros Oriental ang Maritime Training Center at Masters School of Maritime Studies Incorporated. Nilimutan sa may Sambalita Negros Oriental. Sa mga
I think you can mute others except the speaker.
Bisita sa inyong marketing office. Kaya sa may
Kumar, please mute Rosie Jane.
container yard. Pagkita,
Okay, Dr. Kumar, you need to unmute, yeah? Thank you.
It's done. My voice is audible.
Yes, yes, please.
Yeah.
Yes.
Yeah, thank you. Thank you so much. And thank you so much for giving a great opportunity to interact on this, the emerging technology, what exactly we are doing right now currently. Right now I'm in South Korea and working with some projects along with the Hyundai and doing a postdoc in Guangzhou Institute of Science Tech. So here my work is basically some specifically on the quantum ERP problem, and obviously the quantum computing is far away from like many applications, and the connected with the somehow is a communication, all that. So this the topic is more concerned behind that what exactly we are trying to propose here, and this is my actually the future the work is proposing the channel, and specifically on the quantum channel. Means the people are working with the CQ channel. Now we are talking about the QQ channel, that is a quantum to quantum. So the topic is itself is the quantum Schrodinger channel for secured communication. So as you know that the all people are basically those who are working with the quantum field aware about this the quantum terminology that come from this the motivation behind that, and all the stories coming this. So why I started the journey behind that, and I basic understanding about the physical things. If you are actually somebody or the people are working on the atomic and subatomic level, then obviously the classical computing is not so much precise and accurate also. So the understanding about the quantum is basically it's a mathematical framework and to hold the description of the construction of the, or a description about the physical theory. And that physical theory is popularly known about the quantum electrodynamics, which was presented or proposed by famous scientist and novelist Richard Feynman. So I'm also so much this motivations, and I'm doing this the quantum computing area from the last almost 10 years. And description of the quantum is obviously these two scientists is always is in the pictures, and that's why the coming is the Schrodinger and interaction pictures. So the based on this quantum interaction is basically divided into two sections. One is a Schrodinger interaction picture, and other is a Heisenberg interaction picture. So these two scientists is separated based on the operator and state. And my more work, concern or my inclination toward the Schrodinger's pictures basically. So we are dealing with the quantum states, and in the idea behind the quantum state, I always not so much focus for the operators, that is a momentum. So as per the Heisenberg interaction picture, they told about that. So you can deal with the operators, that is a momentum, and you should concentrate on the state at this potential. But as I told that obviously my working is somehow is Schrodinger interaction. So I am working with this the description behind the energy state, eigenstate, on all that. So whole this process or whole this presentation is more concerned or inclination about the Schrodinger interaction or Schrodinger states. So these are basic story, and everybody's understand that story from the quantum like pictures or quantum development of the quantum computers start from the Feynman, and then the many algorithm and start showing that the Dutch David and the Peter Shor and Grovers. And obviously in last year, in all the quantum community is like so much, obviously when these three people got the Nobel Prize and talks about the experiment of the entangled photons and how actually the establishing the violation of the Weyl inequality and all. So as I told that it's a basic things. It's all about the representation of the quantum and classical. The classical is all about like a switch. It's on and off like one and zeros, and so like a binary. But in quantum it's working with the summary. It's not like a on and off. It's working with somehow the both is 0 and 1 is simultaneously working. So that's why we call the superpositions. So this superposition is like looks like that. So the picture you show that this picture is nothing but it's actually the movement of the electrons, actually the showing that how actually electrons is moving to up spin and down spin. So this is nothing but it's a state, and this state is basically showing our quantum states. So in quantum computing or quantum applications, we are actually the combination of the superposition. But three properties very important. You should understand that the superposition, entanglement, and parallelism. So the basic, when you start the quantum computing or quantum something, you can understand how the superposition basically. So in classical, everybody know that the superposition means it's satisfy the two condition is a homogeneity and linearity. So same like that in quantum computing. If you explain or if you draw the quantum state wave functions in 0 and 1, then again the two terminology it will come in the picture, like homogeneity. That means there is some coefficients on some basis functions. We are actually the with the cat 0 and cat 1. So I will show later on. So it's the same thing as per the definition. This is a classification of the classical bits, and it's a quantum computers. I mean qubits. It's a see that. This is at the same time you can see that the 0 and 1s are coming in the picture. So means you are the possibility of what exactly is based on the probability. So if you talk about the mathematical terminology or the states, how actually it looks like that. The quantum is like a classical is showing the states number of in bits, how many actually processor we can operation time is based on that, and in quantum is like 2 to the power n. So if you understand the difference between the classical and quantum. Simply, why the people are actually jumping to the quantum world or quantum world is simple. The first is the time. It's exponentially. It means convergence time is much faster than as compared to the classical, because it's ordering is something somehow the logarithmic or exponentially. So that's why the quantum computation is much faster, or computation is very faster as compared to the classical. So these are basic representation. I am showing that. So every qubits are two possible state, and cat 0 and cat 0 and cat 1. So you can represent this notation as a bra also, because the bra and cat are complex conjugate. So we are not bothering about which actually representation we are picking that. So either you can choose at the cat form or in the form of the bra form also. So and the second is cat psi. It's a wave function representation of the wave states. So it is nothing but it's a alpha cat 0 plus beta cat 1. So what exactly the meaning of this, the significance of this these two actually functions? As I told that all the quantum systems is basically it's a orthogonal computations. And if you talk about the representation, so how actually cat 0 and cat 1 is like in terms of the matrix. So it is like a representation of a cat 0 is 1 0 and cat 1 is 0 1. So that's why somehow it is a representation, means that is a matrix mechanism. So somehow is a quantum computing is also a matrix mechanism, and which proposed first time is was Heisenberg. So Heisenberg is basically all the talks about how the matrix mechanism will implement it through the quantum computing. So these are just simply I am showing this. If you have some states cat psi and cat psi b, and these a and b are just nothing, it's the basics. And the mod of, it means all you taking the probability, I mean a square plus b square and so on, is sum of is equal to 1. That means what is the significant, or what is the meaning of this 1? Means the quantum states or quantum system, it's actually operating in that the unitary of functions. So if you understand the postulate of the quantum system, the first postulate talks about the quantum states. I mean, how actually it looks like that, or how actually you can showing the quantum states. Second is actually evolutions. Means if you are putting the wave function into the box, and that box is behavior, the Schrodinger dynamics or quantum system, the output of the box should be, ideally it should be unitarity. Means all the quantum systems should be identity, should validate to the identity. So how it will be identity based on that the matrix, actually the probability of all the basis functions, means a square plus b square, that should be 1. So somehow the quantum computing, again the probabilistic mechanism. So it's expression of the matrix. That's why we are calling the matrix mechanism. If we express in the form of the probability, that's why we call the quantum probabilistic mechanism. And if they talk about the relative phase and all, the magnitude is always all the state, all the in every phase, and the states are always 1 because the magnitude is 1, but the phase difference somehow is the gamma is like. So this is the representation is what is the relative phase between the two quantum states. So this expression is showing how it's different from the relative phase. So these basic things. It's as I told that all the quantum operations is the reversible, and Boolean operation is somehow it's not and not. I mean, possible somehow is necessarily to they are validate the reversibility, somehow is irreversible also. So this is a basic concept. It's all the reversible operations should be unitary. So quantum system understand that means the output of the quantum system should be validated. The unitarity should be understood. So ideally, it is proven that like okay, you can submit you can put the wave function into the box, and then the output is like that. So what is the unitarity matrix? So this is how it looks like. If it is satisfied, the U dagger should be identity, then it is a unitarity matrix of the quantum system. So this is the basic mathematical model. I am explaining, not so detail in here, but I want to explain how actually the concept behind the Schrodinger terminology I can pick that. This you can see that the equation is second equation is somehow it is actually the I am explaining in terms of the unitary evolution techniques. We are just replacing the wave function psi in terms of u, and that's why this is the first order Schrodinger equations. And it's nothing but it's a simple differential equation, and you can find the solutions of this wave equations and this unitary equations. It's somehow it's an exponential complex signal. So that's why initially I told that the quantum is a mathematical framework. This is a mathematical framework, and that whole the mathematical framework described by wave functions. So how it is wave function? The similar like a wave means electromagnetic wave, and how it looks like obviously it's a complex conjugate. E to the power minus something, how is e to the power I t h. If you just consider the h0 plus epsilon vt is a one single Hamiltonian, then this is the basically and you can find the solution of this ut. So I just proposing why actually how it looks like that. What is the mathematical model of any of the quantum application? What is the model of the quantum Schrodinger's equation using the unitary evolution technique? And you can solve it, and you can find the solution behind the Schrodinger equation. So the basic question is, which system are basically you can implement it? I mean, whatever the system you are picking, like a three-dimensional harmonic oscillator, ion trap, Rydberg atom, or photonic pairs, any of the system or superconducting qubits, you have to understand that what is the Hamiltonian of the any system. So as per my actually the area of research and what exactly you are doing here, we are trying to find the Hamiltonian. And so if you have a Hamiltonian of the any quantum system, you can easily cope up with the quantum properties, and you can find the wave equations, or you can find the solution of the unitary wave evolution techniques through that, and you can solve this problem. See, these are actually the things. How actually you can find. See, this is the this equation is basically 3D harmonic oscillator. Means I said that you can choose a single harmonic oscillator, you can choose a 3-dimensional. So the basic system is a harmonic oscillator, and based on that, if somebody are initiate on the quantum system, always they are picking to somehow the harmonic. Then after that, you can change the system either in the Rydberg atom or somehow ion trap. I also use, and some paper I published on based on the ion trap. And recently, I'm also doing on this the concept on this ion trap based something quantum computing on 5 qubits. So these are basic things. So the basic concept, you have to try to find the potentials. So as I told that the Schrodinger is mainly focused on the states. So the state lies on in the form of potentials. So these are just solutions how actually we can use. Now I am just highlighting one very important thing, that is the Dyson. Why the Dyson is more important? Because the quantum system is basically it's lie on the infinite domain. So is it possible in practically this infinite domain quantum system give the unitary? No. So how it will be unitarity? So you have to truncate. You have to truncate that, and truncation through the truncated Dyson teeth. So Dyson was also one of the greatest scientists who can actually implement it. Yeah, definitely he did not got the Nobel Prize at the time of Dyson, Feynman and Tomaga and Swinger, but he gave a great, methodology to validate that unitarity concept and to get that unitary evolution. So I use mostly in my research, I use the truncated Dyson series to actually verifying that derived unitary gate to matching with the desired unitary gate. So this is the solutions, how you will get this Dyson series solutions. If somebody are interested on this area, so how actually practically you are actually verifying this your output of the quantum system validate to the unitarity, you can use a truncated Dyson series and showing that your output. Now come in the picture, because as I told that simply, the quantum Schrodinger secure communication. So the last, I already explained what is the quantum, why the Schrodinger is implemented, because that I explaining, because the two parameter is operator and state. So you can choose any of this, and this then you can pursue. So quantum Schrodinger channel, we are trying to actually implement on the Schrodinger. Channel is the quantum also. I have already published one paper on quantum receiver. So that means I did that. So how actually you can implement? So simply, if you understand, I said that if you understand the Hamiltonian and what is the function of a Hamiltonian, how it looks like that. Hamiltonian means what exactly? It is somehow is unperturbed, means without disturbance, without any disturbance, you have some energy. And after time t, you have some disturbed energy, like a perturbed Hamiltonians. Okay. So in classical communication, what is exactly the function of the classical? You have some carrier signal, you are modulate with the signal and transmit it. This is the basic concept of the classical communication. Same like that in quantum communication also. You have a potential, like if you see this equation, the last equation, ht is equal to h naught plus epsilon in p and v. So v is what exactly your weak interaction potential, and thus v is actually modulate with your massive signal. This is the in p and it's a PAM signal, pulse amplitude modulation. I use here, I'm using this equation is like a verified the pulse amplitude modulation. So what exactly here I'm doing? So this V is basically modulate with your massive signal and combined with your unperturbed Hamiltonian and put into the quantum system. Okay, so this is the basic philosophy actually, where how actually we can pursue and how we can start from that, and then we can find the channel estimation techniques and to get the to verify this the channel quantum Schrodinger channel and showing that. So here I use one more terminology. That is basically the entropy. I mostly I find the entropy. So entropy is obviously the classical is entropy, Shannon entropy. But again, there is some drawbacks and some of how is yes.
Dr. Kumar, you have your last 5 minutes, yeah?
Yeah, sure. I will complete that. Yeah. So somehow is very important is, there technique I use mostly is left-hand theory, and that is more famous theory, and to implement this quantum Schrodinger channel, and is very useful that. So overall, my concept is basically we are dealing with the mixed state. So quantum channel is basically talks about the how actually you are actually implementing this. So I am showing one diagram. So the very you can understand the whole the picture. This diagram is very useful. See, there is a receiver transmitter side, the Alice is sitting, and on the receiver side the Bob is sitting. Now you want to transmit the information through the Alice to Bob, but in channel there is some another state that call is the EVA, and in quantum we are calling the Bath state. So somehow if you are interacting with some Hilbert space with the Bath state or somehow, then it is violated. It is you lost the actual information. So the question is how to deal with the Bath state in the quantum channel. So I use there the Hudson-Partha-Sarthi equation to estimating the noise and to establishing the quantum Schrodinger channel for the secure communications. So this is the basic one diagram actually where the Chinese actually I use that. Even India is also obviously DRDO did that, and some of the like PRL they are also Professor Arvesina, they did that also. Some experimental side of the quantum communication. One lady, there is a Professor Rosi Sinha, she's also working on this side. So many of the people in India also, they are working on the quantum communication side, and they already did some experiment on this on this secured communication. And most obviously hopefully in now coming days they prove that then somehow is the satellite communication, how they could transmit the entangled photons pair and somehow. But my basic and the last is how actually is, if somebody are interested in the atom side, there is also many hope, and we can also do that. I mean, right now the people are all globally, they are working on some photons pair, somehow. I am trying to actually cope up with some atom side also, and we are trying to, my research is more focused on the atom side. So let's see how actually we can implement through the atom also. So these are basic things, and these are actually a prospective area where you can actually work with the quantum communication, or somehow how actually you can implement the quantum. So there is a vast area in the quantum, and you can implement in anywhere, not only the communication, but here we focus with the major focus in how actually you can transmit the secure communication and somehow. So this is my actually the startup we working on this somehow is like in India. I started 2019, and obviously I got some fund also and some collaborations also we needed, and we work on this quantum computing and communication side. Thank you so much.
All right, thank you for the insightful sharing, Dr. Kumar. So that was your postdoc engagement. So
Right now,
maybe
yeah.
any questions from the floor? Maybe one or two, if there's anybody would like to further contribute any questions? Okay, you can probably put it in the chat box if there's any. Meanwhile, thank you so much, Dr. Kumar, for your insights on what's happening on your research and also on quantum communication. So without further ado, I do not see anything on the chat box. So thank you so much.
Thank you so much.
Let's see, yeah. Dr. Nick Zulkarnaen, are you there? We had an introduction.
Yeah, I'm here.
You're already there. Okay, your brief introduction has already been read in the first session just now. So I do see you online. So just a recap, like I said, Dr. Nick Zulkarnaen is from University of Malaysia, Kelantan. He's a founder of Creative Action Lab, University of Malaysia, Kelantan. He is a digital technology consultant, so he has 20 years experience, and he's also won various outstanding entrepreneurship mentor awards. And he's known to be a certified entrepreneurship coach, also a trained computer thinking design consultant. So without further ado, Doctor, you are given 20 minutes to present. So I hope you could stay in time, and all the very best to you. The floor is yours.
Okay, thank you very much, Dr. Yuktha and the floor. So I'm not getting to the technical part of how this quantum communication computing technology will be applied. So my presentation would be to see the potential, what can be done by having this type of technology in terms of business and opportunity, and also to be implemented at industry. So can you see the slide?
Yes, Doctor.
Yeah, so basically everyone have know the concept of quantum computing. It's about how we can make a lot of advantages by having this technology, so that we can produce a more high capacity computing power to execute a lot of calculation. And then we can see this potential can be implemented across of industry. And we believe this type of technology can give benefit not only to the researcher, but then also to the industry and also the public user. Like we having this current technology, the computing technology we have implemented, but maybe in the future we can implement the benefit of the quantum computing on application side, especially for industry. Okay. So what I interested, they have if we can harvest or we can create a more powerful computer by having this quantum computing technology, we can solve a lot of industry issues, especially the challenges that industry facing towards the creating more application. And we can see the opportunity for this technology that can help the industry and the future move of the technology. So I just want to share some application that will be useful and will be have a potential. For example, we can apply this quantum computing technology in artificial intelligence and machine learning. So we can develop a lot of application with this the powerful computer so that we can manage and we can process a lot of data by utilizing this technology. And we also can see the application on drug design and development. Of course, just now Dr. Kumar has explained about the cybersecurity. So how we can adapt this technology to strengthen or manage the security issue, cybersecurity issue, as well as in financial modeling, weather forecasting, logistic optimization, and computational chemistry. And as we know the potential of this quantum computing that they have implemented in some cases is still at early stage as far as constant. But if we have this vision or this move, we can plan what the industry requirement that be ready to adapt this technology. So this is what I can see from the development on the technical side of quantum computing, so that in the other side of implementation or in industry, they can adapt this technology so that we can have a best fit for both worlds. The technology can develop, the technologies can develop the technology, and the industry can enjoy the benefit get from this technology. And in terms of drug design and development, we can design can cut the cost of processing some of the process by having this kind of technology. And by this quantum computing can be a powerful method to understand medication and their reaction on the people, and save a lot of money and time, so that we can commercialize this technology. Hopefully, by having all the experts in quantum computing, we can contribute towards the benefit of industry, especially in healthcare and design the drug. And as Dr. Kumar has highlighted also in cybersecurity and cryptography, there's a quantum computing approach. They can strengthen the security aspect so that we can use this quantum computing with the combination of the machine learning. We can have to build an encryption method known as a quantum cryptography. So this is a lot of potential you can see, but whether the industry are ready in terms of cost and everything, this is something that will be explored more in the future. And as another example of application on industry issues, we can apply it in financial modeling with computing in quantum computing, whereby we can analyze more critical portfolio analysis. Okay, we can process now we have big data and we have a lot of data. So with the powerful of quantum computing processing, we can manage to analyze all the portfolio analysis, as well as fraud detection, optimization, the process, and also they can strengthen the cybersecurity system. And sometimes nowadays there are a lot of frequency on trading, so they can manage all these processes, and also asset valuation. And also we can see also this technology can use as in weather forecasting. Okay, so we can process more faster, and we can solve a lot of problem by having more accurate forecast on quantum on the weather. And as I mentioned also, they have the application on logistic optimization. Okay, by having this quantum computer, they can improve the speed of process, and also can have the energy. They can use less energy by having a faster processing part. And with this quantum computing also, we can apply to optimize the logistic process. Okay, for example, we can have the advanced dynamic route optimization, and can maximize simultaneous packing and parcel, and also to support the adaptive reallocation of asset, as well as enable quick testing for designer and material for the logistic use. So this is I think the industry need this technology to improve their services and process, so that all the operation unit for this process can more efficient in terms of producing the services. We can improve a more a faster service related to logistics. And this is whereby we can have a faster delivery, and they can improve the time of processing. So this is one of these advantage that if you can use or apply this quantum computing technology. And there are some opportunities and strategic moves beside all those applications that we can foresee that can be implemented or practiced in industry in the near future. But we have to educate the industry slowly to adapt this the development in research, especially in quantum computing. So I have see some of the steps for your quantum future. We have a 5 strategy. The first step, you need to find a champion. Who are the technology developer? Okay, who can have the expert in this industry or this technology, so that we can groom all those champions, so to produce more innovative and development and research, so that they can offer the solution, okay, for the industry. And the second step, we need to identify the use cases where we want to implement. So this is quite a strategic move from the strategic move, how we're going to adapt the technology. We need to identify the cases as a maybe a pilot project, so that we can implement a small scale of the implementation. It's still under some cases that really worthy to implement, and there is the return of investment to implement on these cases will be not so long. And of course, the third step, we need to have some experiment. Of course, when to implement these use cases, we need to do some experiment to make sure the system, the technology that we use and develop can be suitable for that particular industry or cases. As I said in the previous slide, you can implement in a lot of industry and various type of application. And the fourth step will become ready for quantum to be commercialized. So I don't know where they can be ready for industry to use this technology, but then we need to have a plan to make sure the industry are ready to adapt the new quantum computing technology to be adopted in industry, like we having now new technology. From the beginning of computing technology until now, they have a lot of development in terms of the hardware, in terms of the algorithm software and everything. So you need to adapt from the strategic perspective. So this is what I can see from understanding the industry and the technology set. What the strategy to make sure all those research contribute from all the researcher, from Dr. Kumar, Gary, and all the industry over there, so that we can easily commercialize. So because the industry understand the opportunity and the development that we have, so we can implant into the industry, so that we can having benefit to the industry. And for the last step, at the stage of flexible adapt, so we can have a quantum advantage, so that the quantum technology can be like a normal use in industry. So we need to consider about the market development, how and when this technology can be widely used by the industry. So of course, we need time, so that we need to chart a strategy, so that we can see from both perspectives, not only from the technical part, but we can see from how we're going to implement and commercialize this technology towards the development of the industry. And this is another detailed step how we can plan for the strategic move for future quantum technology. So as I mentioned, we need to be select the champion, we need to assign some quantum champion. Of course, every expert or researcher, they have their own expertise, so that we need to know, so that we have the technology and we want to identify, okay, the use cases to recognize where to be implemented. And I think I already explained all this. Maybe I just recap on that. They have need to develop a quantum ready for the industry, and experiment, of course, the flexibility of adaptation, and so on. So for the next, I just want to recap some of the adoption on quantum computing in banking. For example, in the banking, if we can manage to process all those data, we can targeting on a prediction about 25% to small and medium-sized financial client. So because they have to manage a lot of data, a lot of account, so that by having this technology, they can effective, they can productive to do some prediction and target based on their account, because the account of the user is increasing every day, so that we can have a so powerful computer that can manage faster on this data, the very huge data. And we also can apply the benefit of this quantum computing technology in terms of risk profiling, because as we know, when we want to produce or analyze the risk profiling for the risk, they have lots of possibility, a lot of ambiguity, so that we can every single situation or a possibility of the risk need to have a proper profiling. So this is need a more powerful computing power to manage all the data. Okay, and of course we can manage the trading optimization. So when to predict the market share, so this is some of the we need some computing technology power to have this to manage all those processes. And another things that we need to see the potential of this quantum computing technology. We need to apply this technology on financial problems. Okay, for example, to improve the venture game. How are we going to improve the venture game so that this can be an advantage for this financial institution, so that they have a better infrastructure, especially on ICT infrastructure, so that they can have the advance from others financial institutions, and they can reduce the capital necessity, so they utilize all these processes by computerized system, and this can be an advantage for that institution, so that they can open a new venture opportunity more frequent. And also we can improve and distinguish the proof of the executives from the hazard and consistent. So this is some of the figure that I figured out. By having this, we can increase the numbers of revenue potential by several processes or activity. For example, we can have this fraud detection more faster, and also forecasting a financial crash. Okay, we need the infrastructure that will be very good to analyze all these data. And another thing, quantum computing technology also we have the opportunity to be implemented in healthcare industry. So this is some of the example what we can do in healthcare industry by having this quantum computing technology. We have supersonic medication plan. Okay, we have reached a period of psychoclinical trial. Okay, sequence analyzing DNA for full speed, so we can analyze faster all these process of analysis, and some making patient truly point of care, so we can improve the process, the operation in healthcare processes. So I think we also can. They have some question. Okay, decide they can serve to big enterprise and so on. The quantum computing can also have in terms of enterprises. For example, to cut the development time. Okay, for chemical. Yes.
Excuse me, Doctor. We have approximately another 4 minutes to go. Yeah.
Okay. So just so we can
Sure.
solve optimization problem, and we can accelerate the autonomous vehicle as well. Okay, by quantum AI, and also we can transform the cybersecurity approach, okay, for improve the encryption and to increase the what we call it, the security level. Okay, because now security is another concern as well. Okay, but we need to have those technology that can support, okay, the processes. And of course, in cloud computing, some of the elements that we can adapt is quantum computing. Of course, about the speed, about the processors and so on. So this is also can be implemented. So I can see this opportunity to produce a more better services, cloud computing. And in terms of the hardware, I think they need to be more, they have need to be ready lah in terms of hardware. All these technology that will be in line with the hardware development. This is another example how to see to solve the complex simulator to solve the complex problem. And the roadmap we can see maybe from my reference, maybe the potential to be integrate on quantum computing in the business would be another less than 10 years, about 2030 and above. So this is the movement, how the roadmap, and how we plan for industry to be ready to adapt this quantum computing technology. And the roadmap will be, we can plan, okay, but we need to have enough researcher or resources that capable, okay, to make sure all this research can be commercialized, so that the industry can enjoy the real benefit of this technology, so that the business can be grow better, and the society that enjoy this solution can be get the real benefit of this technology. And I think this is my final. By having all this, we can have a very good cryptography, cryptography technology in aviation industry, data analysis, forecasting, pattern matching as well, medical research, and also this self-driving car. And there's a lot of things to do to find out the best case study that we can have pilot to implement those new research or potential application in the future. I think with that, thank you very much. Okay, so you have any question, or maybe I think that's all from me.
All right. Thank you very much, Dr. Zulkarnaen. So that was insightful on what's happening to the current industry. There's a lot of usage of quantum communication I see there. Okay, so any question from the floor? Again, to the dear members that was listening to this seminar, if you would like to have any questions, you're most welcome to post them in the chat box as well. So for those of you, gentle reminder, please mute your mics, because we would like to hear the speaker clearly when he's delivering his content. So once again, thank you very much for your insights, Doctor. I do not see any questions on the chat box, neither questions from the floor. So without further...
Thank you very much, everyone.
Yeah. I would like to call upon Mr. Santanu Ganguly. Mr. Santanu, are you there?
Yes, I'm here. Can you see me, hear me?
Yeah, I can hear you very clearly. I'll give you a brief introduction before the floor is given to you. So warm welcome. Today we have Mr. Santanu Ganguly. He's experienced at pre and post-sale delivery, currently with Quantum Information and Security Research, Protonic London, UK. Okay. His interests including quantum computing, quantum machine learning, post-quantum security, data centers, cloud architecture, cloud security, automation, and orchestration. He's a member of a Responsible AI Institute and is also a patent review of quantum computing related proposals at Cisco. He was a Court of Creative Destructive Lab quantum machine learning participant in 2020. He is a reviewer of books on quantum computing and machine learning. I see a lot of computer knowledge in here with him. His keen research on dark energy signatures and quantum gravity. Okay, without further ado, I would like to give you the floor. Again, a gentle reminder, you have 20 minutes to present your talk, and we hope to have questions from the floor. All right, thank you. The floor is yours, Mr. Santanu.
Thank you very much. Please bear with me while I try to share my screen. I hope you can see my screen actually in presentation mode.
Yes, you can put the full slides. Yeah, okay, clear.
Yeah.
Perfect.
All right, excellent. So I have a lot of slides here, which I will definitely not cover in 20 minutes, and that's not my intention either. The slides are there just for references, and also with my previous and other speakers who will come after me, there are some overlaps in terms of QKD, etc., which I will skip. I'll just refer to them, but I'll skip and defer them, the subject matter, to the proper experts. And before I start to talk, thanks a lot, Dr. P.Yukthamarani, for moderating this. And it's a pleasure and an honor to be here and to be able to speak. Thank you. So, why quantum technology? And why should we care? And then I'm coming at it not from a purely research point of view. I am one of the participants of CQN, the Center of Quantum Networking, which is a consortium of about 8 to 10 universities and headed by University of Arizona and MIT in the US. So basically, our point of view is not strictly research based or not strictly industry based, but it's kind of a hybrid, right? So why quantum tech and why do you want it? So my previous speakers have spoken at length about why quantum tech and why do you want it. Our point of view is, if we consider the complexity, the cost of a quantum platform that exists today, I won't even touch on the diversity. So, for example, DOF Systems was selling their annealing-based platform 5-6 years ago for $15 million per platform. So if we think about that today, then be that quantum communication, be that quantum computing, be that machine learning, the question arises, who's going to use this? In other words, are we going to copy paste using a quantum computer in the next 10 odd years? Are we going to download PowerPoints and then look at them on a quantum computer in the next 10 years? The answer is likely no. Why do it when I can do it on my laptop, which costs less than 0.0000001% of a quantum computer, right? You don't need it for that. So chances are that quantum communication, one of the reasons we at industry, as in Cisco, as in Photonic, as in Juniper, and then several other vendors right now as we speak, have become interested in quantum communication itself specifically, is from the point of view of security. That's the #1 application. And then there is the big question of general quantum communication. Quantum tech and quantum computing has an amazing amount of power, as pointed out by by Dr. Kumar Gautam, the first speaker today. And the power is currently not just the speed of computing; it's also the power of multidimensional computing. As he pointed out, the concept of superposition and entanglement gives quantum computing the power of parallel computing by default. Parallel computing is something that we use, for example, supercomputers today to perform specific tasks. And if you have, for example, a 50, 60 qubit quantum computer, that actually is offering you the same property by default. So that's one thing. And that's scary from the point of view of security, number one. And if it's scary from the point of view of security, it will also be scary from the point of view of communication and encryption, and how it can break existing encryptions. So yes, so this is something that we have not seen before. We are familiar with binary platforms that do computing based on binary, but we have not really seen this. So this is something coming, and coming from all directions, be that from superconducting platforms, be that from photonic, be that from ion trap, it doesn't matter, but it is coming. And it is a beast we have not seen before. We actually don't know currently. We are not 100% sure how to handle this. So I'm a big fan of Mandalorian, so obviously I borrowed this from there. And yes, that's the Mandalorian striking down the Crave Dragon on Tatooine. Now, so this is why it's very important, not just computing, not just machine learning, but also communication. Now, what's in it for us, and why quantum at all? So, as you may or may not know, NIST and NCSC went public in November 2020, saying that between 2022 and 2024, all enterprises should implement post-quantum crypto. Not necessarily quantum key distribution, but post-quantum crypto to protect themselves from quantum attack. And 2024 is not that far away. It's like, what, 6 months away? US government, federal government actually gave, sent out, and also UK government, with whom I work with quite intimately, sent out RFIs, actually request for information on to their vendors, requesting information on where they stand in terms of offering security against quantum attacks. So focus is on networking, hardware, software, security, machine learning, and algorithms. So yes, so this is the road to future. This is coming. It's no longer a teenager's dream like it was when I was growing up. And the best way to predict your future is to create it, said Abraham Lincoln, and that's one of my favorite quotes of all time. And one of my favorite people of all time is also the screen, which was Albert Einstein. Why now? I'm not going to go into business side of things, because obviously Dr. Nick spoke about it at length. But there's been a humongous investment in startups in recent years from government, and specifically China and the US, and also European governments. And US, President of the United States famously signed off on a $190 billion budget in 2022. So yes, this is amazing. This is great, and even from not just from a research perspective, but also from a business point of view, because vendors and people who can actually deliver this stuff first up is going to get the largest chunk of the pie. For example, that $190 billion pie, and that's not a trivial amount of money. Again, I'm going to skip this superposition, etc., because again, this has been spoken of before. This is just a quick visual to actually grasp the power of quantum computing as opposed to our standard computing binary as we do today. If we wanted to count 2 to the power 20 to the power 64, basically in 2-byte increments per second, it would take us about 400 years. But if we wanted to do that on a quantum computer, we should be able to do it in parallel all at once. And that's basically the power of it. So a standard computer, think of yourself in the middle of a puzzle where you're trying to get out of the puzzle via various paths, but only one path lets you out. So a standard computer will take you path by path by path by path till you find the actual exit point. A quantum computer can basically estimate that and calculate that, everything all at one time. So that's why we need the importance of it. So the other side of very important property in communication and computing for quantum computers is entanglement, as spoken by Dr. Kumar Gautam. I'm not going to again expand on that. But what entanglement does give us is the property of quantum teleportation. Now, a lot of us, when we were really small, grew up watching Star Trek on TV, where Captain Kirk would say, beam me up, Scotty, and Scotty would, beam him up from strange planet to the Enterprise, or from the Enterprise to some strange planet. Now, is that what we mean by teleportation? Well, not right away. Right now, by teleportation, we mean using the property of entanglement and using that as a payload with the existing entangled qubit. Measure the result by Bell measurement, which destroys the payload and the entangled qubit, and then transfer the bits from read on classical comms channel. So that's where we are. That's what we are trying to achieve in real life, in reality, in communication, in industry, and research industry intersection. We are not going exotic where we are trying to transport a person from one planet to another. We're not there yet. We don't even know how to get there, to be honest, right now. So without much further ado, use case for molecular simulations. Yes, a penicillin molecule has 48 atoms. You need 10 to the power 86 classical bits, and you need 286 qubits. I have a cup of coffee here. A caffeine molecule with similar estimation. A caffeine molecule takes, I think, about 10 to the power 5 classical bits. Then you can achieve that like in something like 100 qubits or something. So yes, it's quite powerful, and that's why we need it. We need it for molecular simulations. We have applications in financial sector, which Dr. Nick spoke about before me as well. And in financial sector, the adoption has been absolutely massive. So as we speak, Goldman Sachs have a QC research team headed by Dr. William Zhang. JP Morgan has a similar one. Morgan Stanley, Bank of England, Barclays Bank, HSBC, they all are investing in quantum computing from a perspective of development of algorithms and machine learning, focused on risk analysis, focused on portfolio optimization, focused on certain other banking applications, and definitely security. Okay, that's one of the major things. Supply chain, yes. Communications, yes. So massive adoption in financial sector. Going forward, I have some listing of some certain companies. This is borrowed from DUF systems, who actually have DUF systems installed on base for the last 5, 6, 7 years. So Lockheed Martin, Google, NASA, obviously that's well known. NASA is actually using DUF's quantum computing to optimize and model the environment, the weather and environment on Mars. So that code is actually running on the current Mars rover. So I was actually at a congregation, a training with the guy who actually coded it for NASA. So that's Alexander Ghulam. And that's exactly what's running right now on the Mars rover. Then there is defense applications. Obviously, you see Oak Ridge and Los Alamos. They are also looking at it from the point of view of energy analysis. Sorry, Dr. Yukta, am I running out of time? I can't hear you.
You're on the last 5 minutes of the call.
Okay, excellent. I will zip through my slides, and I will leave everything. So this is actually a quick slide on on post-quantum security. Why that's needed? Currently, a lot of the encryption on RSA, not only encryption across the internet, depends on RSA and elliptic curve. So those two are actually in danger of being decrypted and under attack in near term by quantum computers. So there is verifiable evidence right now that certain geographical locations, without mentioning any country, are right now mining encrypted data with hopes of decrypting them in the next 2 to 5 years once quantum computers or faster computers become available. This is a massive threat, not for you and me, not for people with credit cards because they'll expire, but for governments and financial sector because they have encrypted data that was never meant to be visible for public eye. So you can think of Edward Snowden or WikiLeaks on steroids. Going very far again, I'll leave. I'll skip the post-quantum crypto and stuff for people who are actually coming up after me. One of the biggest challenges in quantum networking and communication right now is the standardization. So there are various standards bodies. ETSI in Europe is one of the leading ones. IETF KIRG, we are members of that. ITUT is also looking at it, and IEEE as well. So as long as the things are not standardized, we can't really put it out there on an existing communication network, which is internet. Which takes us back to my first question, which is quantum, be that quantum network, be that quantum internet, is this going to run one fine morning all by itself? It won't. The first thing that we have to do in industry is actually build it up on top of our existing network. So for the next 10, 20 odd years, quantum internet, quantum networking will likely be a hybrid. So built up on top of existing networks and actually, the stack, there needs to be a stack on top of it, the software stack that will also very likely be, classical stack. So yes, that's something what we're looking at. We're looking at regenerator and replicators for quantum networking implications, because there are distance limitations in quantum communications, which many of you know, because signals on modern current optics basically suffers from decoherence after a distance of 50 to 60 kilometers. Quantum internet, so I'm going to flip through all this, and the main points is the stack that is being defined by ETSI QKD01 for REST API is something that we are working on, because that is something that will give us visibility and resource management of a quantum network once it, or that's a quantum classical hybrid network when it first becomes available. The biggest question is what kind of quantum computers are connecting between each other? Are they superconducting both on both sides? Are they superconducting and photonic? Are they superconducting or an ion trap, or a combination of all of the above? That brings into question, how do we get that information generated by the quantum, that specific quantum platform, into an optical qubit? So there are research being conducted in University of Berkeley and MIT, for example, on flying qubits. Quantum memory, we need quantum memory before we can have regenerators actually regenerating quantum signals on a quantum communication channel. With this, I'll stop talking and open it up, and thank everybody for listening to me, and open it up for questions. No questions. I must have put people to sleep. It must be quite late across the world, across the planet.
Okay, nice presentation, Santanu. It was a good presentation. If there are questions, we'll get it through email and we'll share it.
Thank you. Very kind. Thanks for listening to me.
Thank you. Right, the following one. Can we have Dr. Sulabh Bansal? Are you in?
Yes, I am here.
All right, Doctor, are you ready?
Yes.
Okay, we have an associate professor from Manipal University, Jaipur, known as Dr. Sulabh Bansal. His experience spans more than 2 decades in the field of computer science and engineering, comprise academic teaching, designing course, industrial designs, as well as researchers on government-funded research projects. He has proven capability of doing quality research in computer science and engineering, sound understanding on basic building blocks like data structures and algorithms, develop skill to analyze, design, and develop software solutions in multiple and diverse programming environment. Experiencing in developing and teaching courses in core computer science and engineering subjects like design and analysis of algorithm, theories of formal automata, operating system, artificial intelligence, and computer networks. He has vast programming environment experience, to name a few: MPI, Java, MATLAB. He has also capability to manage, motivate, and guide subcoordinates or students for thinking and working in completing defined objective of academic or industrial objectives. So without further ado, Dr. Sulabh Bansal, the floor is yours. You have 20 minutes for your presentation. So all the best to you.
Welcome everybody. This is Sulabh Bansal. So I'll not wasting much of your time. I'll just start my presentation. That is on. Quantum inspired evolutionary algorithms. So we have been hearing that quantum computing has a lot of power and it has an exponential power to calculate. So quantum inspired evolutionary algorithms will be one of the way which can be used to understand the power of quantum computing to a certain extent. So to start with, I'll just cover or touch some basic quantum computing concepts like quantum bits and superposition. So quantum computers, classic computer, if we compare classic computers with quantum computers, the quantities which are used to represent information in classical computers have been voltage or current or something like that, which are physically measurable. But in quantum computers, the the physical quantities which are used to represent information are represented by a nano, like very small quantities like electrons, spin of electrons or photons. So which if we try to measure, they will not be able to measure them accurately. So that is the point, like when they exist before measurement, they exist in superposition. So quantum computers are used to be based on strange principles of quantum mechanics. So what is that quantum mechanics? In a quantum computer, one qubit or quantum bit could be both 0 and 1 at the same time. That we have been hearing most of the time. So what do we mean actually by it? So if we represent quantum bit or classical bit by coin, so classical bit will be one face of the coin at one time. So either it will be 0 or 1. So if we are representing two faces of the coin as 0 or 1, they will be 0 or 1 of the face. But quantum bit can be in any phase, like a coin when it is in motion, when we have hurled the coin upwards, then whatever may be the state, it is not defined at that point. So before observation of a quantum quantity, every information exists in this form, which we call as superposition state. There are many ways how quantum quantities or physical may be represented physically. One of them is like we can represent state of a electron based on the state, its excited state or normal state. So it can be in different hemispheres while revolving, and that is how it can be represented. If it is in this circle, it is in one state maybe, and if it is in this circle, it may be represented at 0 state. And then superposition may be represented maybe like if before observing, if we don't know what is this actual state, so it exists actually in both of the states at the same time. And whenever we observe it in only one state. So before observing, if we are having three qubits are there to represent our system, then each of the qubit, if it is having qubit can be represented by this form alpha and beta, where alpha and beta are the probabilities of observing a qubit in state 0 or in state 1. So alpha is the probability of qubit to be observed in the state 0. Okay, so if we are having alpha and beta probabilities to be equal to half, then theoretically this is the system which is represented by 3 qubits. So these 3 qubits have the probability of representing 0, 0, 0 by this probability value, and 0, 0, 1 by 1 by root 8. So every state out of 8 states that may be represented by 3 qubits or 3 bits are being there with certain probability. So that is the magic of superposition.
Amazon delivers something.
Yes.
Sorry. Sorry. Am I able to hear? Am I audible?
Yes. Continue, doctor.
So was there any question?
I think somebody just unmuted. No worries.
Okay. So that was the basic concepts of superposition and qubits. Now, as a computer programmer, what we can do? We have to consider our data in the form of quantum bits rather than bits. And whatever operations we perform, now we have to do it on qubits. Okay, so they can be considered as vectors as follows. So whatever quantum computing is supposed to be, it is supposed to be the operations on matrix. So we consider our data in the form of matrix and vectors. Okay. What type of operations? Now the question comes, what type of operations can be done on qubits? So before observing, we can perform several operations which are capable to change the probabilities alpha and beta. Okay, so there are several operations which can be implemented physically. So the research is going on, but like theoretically, all operations which are reversible can be implemented. And one of such operation is this rotation gate, which allows to rotate alpha and beta. So if we consider alpha and beta, like if we consider a qubit as a vector like this, where these are the axes, and this is for alpha and this is for beta, this is for 0 and this is for 1, then this operator will try to modify this qubit value by this much value, del theta, which will be trying to rotate this vector by this amount. Okay, so this is what rotation gate is. So this is supposed to be theoretically, this is going to change the value of a vector by this amount. So what will actually this change will make? The change will make this value, the probabilities of these alpha and beta will change. So if we apply this rotation operator, we will be able to change the probabilities of observing this qubit in 0 or 1 mode. Okay, now how it can be used? So there are QIAs, quantum inspired evolutionary algorithms, which are modified evolutionary algorithms. So what are evolutionary algorithms? They are generally used to solve optimization problems which are NP hard or which cannot be solved by polynomial time algorithms. Now, how do they solve? They don't try to form the solution from the scratch. What they do, they try to search the solution. So if there are several solutions which can be represented in a solution space, So they randomly start with some of the solutions from the search space and try to see how good they are towards in comparison to the optimal solution. So they try to find better solutions iteratively. So these are iterative processes which starts with the population of solution and try to improve this population generation wise iteratively. Okay, so this is similar to what how natural processes try to improve their generations. Like we have been improving as genetic operators. So genetic algorithms, they are one of the EA algorithms. Okay, so how QAs can be used? Quantum inspired evolution algorithms. What do? Instead of representing a solution, what we start with a quantum bit quantum solution. Like for example, I'll just start with a solution example of a problem. For example, this is an optimization problem, knapsack problem. We have been given a bag of certain capacity, fixed capacity, and there are several items, each item with a certain amount of weight with a value or profit. Okay, so what is our aim? Our aim is to pack this bag with maximum profit as much as possible. So optimal solution, there must be some optimal solution for this problem. Okay, and we are looking for that optimal solution. Within this limit, capacity limit, we have to find items which can be put into this bag and we can earn maximum profit. So our aim is to maximize profit which can be fit into this bag. Now what we can do in quantum inspired evolution algorithm. So basically in evolution algorithm, what we can do, we can have this solution represented by a qubit bit sequence of bits, where one bit, each bit represents one item. So suppose this item is represented by this bit, 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 and this item is represented by this bit. And then each of these bits can be 0 or 1 depending on whether we are including this item or not. So 1 means we are including this item in the bag, 0 means we are not including. So we can have several solutions, 1 0 0 1. So there are how many? 5 bits. So there may be many combinations of these 1 0 1 0 bits in sequence of 5. Okay, so each of them represents one of the solution, and we are aiming to find a feasible solution like whose total weight is within 15 kg, and we have a maximum profit to earn. So this is what the solution could be. And in an EA, we will start with a random number of population, a random number of solutions, randomly initialized, and then we will try to improve using several operators. But what we do in quantum inspired evolution algorithms, we start our population by some certain values of alpha and beta. So initially we will have all of them to have probability 1 by 2. Okay, so to have 1 by 2 probability for each of the item. So these are the initialized qubits for alpha and beta initially. Okay, now when we observe this qubit string of qubit, each of these alpha will give us either 0 or 1. Okay, let's see, we will see how it can be done. So by process of probability observation, each qubit can be rendered into one binary bit. By independently observing each qubit using observation, binary solution is obtained. Okay, so we can use this type of operation to realize or to find one of the qubit, one of the solution represented by the qubit string. Okay, so for example, this is initialized population of qubits, and we have generated the random numbers for each corresponding to each qubit like this. And if this value is less than alpha square, we generate no or 0, and if it is greater than this value, then we generate 1. So one of the solution which we get after observing these. So this is what mimicking the observation part. Okay, so we are just trying to mimic the observation part of quantum observation, where we are generating a random number and we are comparing this value with the probability, and if this probability is less than this, so this is what we are implementing on classical computer. So this algorithm is presently being implemented on a classical computer based on quantum inspired quantum computing concepts. Okay, so now this solution, what we do, so this is another solution which can generate based on another observation. So we try to observe the same qubit in earlier way, in earlier slide this way, and in this slide we have again observed this sequence, and we have found this solution generated from this qubit. So this is the sequence of qubits values, and we are generating this solution. So what we do in this quantum inspired evolution algorithm, we try to update each qubit based on the value which we have observed and the best value which we have obtained. So the value which we have observed using this qubit value and the value which we have obtained, that can be used, and we just try to improve or update the probability of each qubit based on what is the correct value. How does it compare with the best? So if it is 1 and 1 is supposed to be in the best, then this value goes beyond, like the value probability of being 1 is increased for this qubit, and probability of being 0 is increased for this qubit. Whenever this solution is good, or for each qubit, we compare it with the best solution, and then we find if it is 1 is there and 1 is there in the best solution, then we improve the probability of this qubit to be 1, and so on. Okay, so iteratively we try to improve the qubit values based on its fitness with respect to the best solution. And what actually we are doing, we are trying to find best solution in the search space. So using this qubit value, what we are doing, we are able to represent each or entire solution space by single qubit. So in the single qubit, using observing single qubit solution, we can generate each of the solution with some probability. That is the beauty of quantum computing. Sorry.
It's just a gentle reminder. You have your last 5 minutes, Doctor.
Okay, so I'm just going to complete. So this is how the framework looks like of quantum inspired evolution algorithm. So we initialize qubit individual randomly by some value, or maybe we initialize the probabilities with half, and then we observe the qubit values to find or to generate the binary solution. Then we evaluate this solution and we select the best solution. So we always keep the best solution found till date. And then we try to update this qubit based on the comparison of this observed solution with respect to the best solution. And we go back, then generate new solutions, then and we keep on doing this, updating qubits again and again and iteratively. And then ultimately we'll go to the state where some of the qubits will attain value 1, some of the qubits will attain value 0, probabilities, alpha values. And that means some of the qubits are going to be observed 1 at all times, and some of the qubits are going to be observed at 0. And this state will represent the convergent state, and this will represent the best solution found using this iterative process. So this is how we can implement quantum inspired evolution algorithms to find optimal solutions or optimize problems which are NP hard and which for which there is very difficult to find the polynomial time algorithms. Thank you. Any questions?
Thank you, Doctor. So that was very much like sitting into a class of learning. So any questions from the floor? I think, like I said, a general reminder, they can still send in questions through the email to your website. So if it's directed to you, please find time to reply them, Doctor. Thank you for your insightful sharing. Can I have the next speaker? Mr. Arka Mukherjee.
Yes.
Are you
Good day to
there?
everyone.
Good day. So I'll give you a short introduction before I pass the floor to you. So Mr. Arka is a team leader with QKD Hardware at C.com, Quantum Communications, IIT Delhi gold medalist. Congratulations. Experience of more than 10 years in embedded hardware design for telecom applications, proficiency in developing cost-effective and robust telecom hardware to meet the demands of rural India and drive the digitization programs in India. Experience in complete cycle of hardware design, development, testing, integration, support, and manufacturing existence. Experience in designing, testing, and integrating quantum key distributions. Okay. He also states multi-layer BBC design for OLT and ONTs for GPONs. Okay. Excellent oral, interpersonal, managerial, and professional skills by working as a team and independently. Proficiency in VHDL design. Authored multiple technical papers and articles in peer-reviewed journals, international conference, and technical magazines. The floor is yours, Mr. Arka Mukherjee now.
Dr. Bansal, can you please allow me to share the screen because I am not able to share until and unless you switch it off.
You got to switch off, Doctor. Dr. Sulabh, can you turn off your presentation? Thank you.
Yeah, is my screen visible now?
Yes, it is.
Yeah, thank you, Professor Yuktha and Dr. Umachandran for this opportunity to talk on quantum key distribution. I am Arka from C.dot Delhi, and C.dot is basically that telecom R&D center of the government of India. We are based out of New Delhi in India, and we have developed fiber-based quantum key distribution solution. And C.dot is probably the first public-funded organization in India to have a QKD system running live in the field. So I'll talk about the QKD, the background, some of the QKD protocols, the standardization that are ongoing in ITUTs, and some of the standards have already have been freezed. We'll show the QKD done at C.dot. I'll show the QKD applications and I'll discuss some of the future scope of development. So I'll start my presentation with the basics of cryptography. So in cryptography, we have a plain text message and we have a key. Then the encryptor makes it to the ciphertext that is illegible to any third party who is not having the access to the key. And at the receiving end, we have a decrypting key and we can decrypt the message to get the original text. So in any cryptographic algorithm, the main concern is that the key should be safe from any adversary. So basically, we can divide the cryptography in basically two broad categories. One is symmetric key and another is asymmetric key. In symmetric key, we can do the encryption and decryption using the same key. The key length is a bit smaller, around 128 to 256 bit. But the main issue with the symmetric key cryptography is that we need some mechanism to distribute the keys among the communicating entities. And generally at present, it is done by public key cryptography. That is another type of cryptography, that is asymmetric one. In asymmetric one, we have one public key and one mathematically related private key. So this data can encrypted with public key can only be decrypted if we have access to the private key. But the issue is that here we have a larger key length and it takes more time to encrypt and decrypt the process. But the main issue that I want to highlight is that the security of this asymmetric key cryptography will remain compromised with the advent of the quantum computers. But someone may also claim that the symmetric cryptography is also at threat. But the issue is that if we increase the key size, say from 128 to 256 bit, we can counter that effect to some extent. So what is quantum key distribution actually? So quantum key distribution is nothing but a method of key exchange. And the security of this mechanism is guaranteed by the fundamental rules of quantum mechanics. So if anyone tries to tap on your system, we can this activity changes the system property irreversibly so that we can detect it. And this security is information theoretically secure, and there is no mathematical assumption. Like in present cryptographic system, there is some assumption that certain mathematical operation like prime factorization of a large integer cannot be done in real time. or in a reasonable time. But in case of QKD, the security is guaranteed by the quantum mechanical principle, and this is information theoretically secure. And if you see the cost of a data breach, it was around $3.86 million around 2020, and it has goes up more than 10% in 2022. So there is a severe concern on the data, because our data is all over the internet, and it is a very crucial nowadays. And if you see the market research, it is expected that the global QKD market will touch $3.4 billion USD by 2030. So QKD have a great prospect in the coming days. So what are the present challenges? So currently, if there is any intrusion in our system, it may get unnoticed for a long time. So there have been instances in giants like LinkedIn, Facebook. There have been instances of data compromise that are in news. Also, as I told, the security is based on certain assumption, like certain operation cannot be done by the classical computers. But this assumption will not hold strong once we have the quantum computer that is very fast compared to the classical counterpart. And also, due to this quantum computer, the frequency of the brute force attack, the time taken to complete this attack will be very less. So brute force attack is also another challenge. And also, as I told, this asymmetric cryptography is a bit slower compared to the symmetric counterpart. So this is in the left side, we have the basic building block of a QKD link. So we have two QKD modules. Traditionally, one is the transmitter is called the Alice, and the receiver is called the Bob. So they are connected by two channels. One is called quantum channel. So we transfer the qubits, and this quantum channel can be a fiber or a free space or a satellite link. So currently in CDOT, we are using the fiber-based channels. And there is one classical channel for the post-processing and the synchronization purpose. So these two channels together are called the QKD links. So these two, Alice and Bob, together generate the key. And on request of an encryptor, it supplies the key to the encryptor and the decryptor, along with the key ID, so that both the end gets the same key. And in between, if anyone tries to tap your quantum channel, then this key, then we can get notified through some parameters that I will discuss, and we can stop the key generation, and our communication will be secure. So this is basically the building block, this left side image, the point-to-point block. Also, we can extend this concept to a larger network, like a mesh network or a tree type of topology, using quantum relay points or optical switches. So quantum relay is currently under theoretical study, but we can have multiple switches or splitter to have a mesh type of topology. So this is called QKD network, QKDN. So based on the decoding methods and architecture, we can have multiple types of QKD. So one is that based on the decoding method, one is continuous variable, where we use that position or phase quadrature, and that is the momentum quadrature. And in case of discrete variable, we use the discrete variables like phase, polarization, or time being. And one subpart of the discrete variable is the differential phase reference, where the information is encoded in the time and phase of weak coherent pulse. That's the very attenuated laser pulse. Currently, we are using the DPR protocols, that is differential phase shift and coherent one-way in our design. Also, based on the architecture, we can have three types of protocol. One is called prepare and measure, where Alice prepared the quantum states and Bob measures. So this is called a prepare measure. So basically, these DPR types of protocols are also, and the BB84 are also called the prepare and measure. Another type of protocol is the measurement assisted, where we have three nodes. One will be Alice and Bob will be act as transmitter, and there will be a third node called Charlie, who will be the receiver. And this main flavor of this measurement assisted scheme is that the final key will be available with Alice and Bob. And if Charlie is taken over by any eavesdropper or Eve, then also the key will be secure. So this is the main flavor, that this measuring equipment cannot be a trusted node. The difference happens in entangled base, where this Charlie acts as the transmitter and Alice and Bob will act as a receiver. Here also the final key will be available with Alice and Bob, and Charlie will not have any clue of the final key. So currently we are using the differential phase shift QKD that I told. So in case of differential phase shift, we have a coherent pulse source. Then we phase modulate it using 0 or pi phase. Then we attenuate the pulse so that the average photon number each in pulse is much less than 1. So in the Bob side, we have an 1-bit delay interferometer. And based on the consecutive pulse, whether it was a 0 and pi, either photodetector 1, this is a single photon detector, either SPD1 or SPD2 will click, and we have the final key. The second protocol that we have developed, the system based on this protocol, that is the coherent one-way QKD. So in coherent one-way QKD, we use the time bin. So bit 0 is represented by a vacuum pulse followed by a photon pulse, that is called a mu pulse. The bit 1 is the reverse of that, and we also use decoy pulse, where the photon is there in both the time bins, So decoy is used to check is there any eavesdropping in the quantum channel. So here the main flavor is that for key generation, there is no MZI has no role. This delay line interferometer. So MZI is only used to check that phase coherence and using the decoy pulse. So the third protocol that we are currently working is the measurement device independent QKD. This is called MDI. So basically the thing is that quantum key distribution is theoretically secure, but the device that we are using, like the single photon detector, they have some imperfection. And in literature, there are some attacks that have been proposed by exploiting those imperfections. So one is called the detector blinding attack, where one bright laser blinds the detector and they can control how it will behave. And another is the time shifting attack. In that, these laser pulses that we are sending through the quantum channel can be delayed in such an extent that the detection of probability of either 0 or 1 can be increased. So the eavesdropper can have some knowledge of the key. So MDI QKD is designed such a way that these chances of this type of side channel attacks are mitigated. So in case we have 3 nodes, one is Alice and Bob. So Alice and Bob acts as a transmitter. They prepares the quantum states. And there is one Bell state analyzer is there in the Charlie. So after that, we have this final key between Alice and Bob. And Charlie is only acting as a measurement device, as I told, but it will not have any clue of the final key. So Charlie can be also captured by a eavesdropper, but it will not have any clue of the final key being generated. So another flavor that was currently gaining attention is the CVQKD. Currently, we are developing DVB-QKD. But the CVQKD has the advantage that it uses the existing telecom technology. It is more compatible. And the cost will be lower in some sense, that because it does not require the single photon detectors. So it is more resilient to the noise. So when we multiplex the quantum channel using WDM, like wavelength division multiplexing, in the same fiber, because in quantum channel currently we are using dark fiber, but the ability of dark fibers is costly. So CVQKD may have some advantage in some sense. And the detection efficiency of the single photon detectors have around 30% efficiency, but in case of CVQKD, detection will be more efficient, will be around 90%. Also, the states are more easy to generate, that is the Gaussian states. So currently we have the theoretical proof of that CVQKD protocols also. So these are the various standards that ITU have come up with. Also, there are other organizations like the previous speaker told, there are HC, there are IEEE, they are working on different aspects of QKD and quantum communication. So to have the basic flavor of the QKD, these are the steps that that undergoes to generate the keys at Alice and Bob. So first, there is one classical channel authentication, like Alice and Bob identifies each other that this is the legitimate party that I want to communicate. If the authentication is successful, then we proceed to qubit transmission through the quantum channel. And we have the synchronization. So in synchronization, both classical and quantum channel is used. So once the synchronization is done, we have, and qubit transmission is done, we have the raw key. But the raw key, we have some, in the raw key, we need to perform shifting to have a common reference in both Alice and Bob. And after shifting, we check the quantum bit error rate. This is called the QBR. And if the quantum bit error is above a defined threshold, then we need to abort the communication, because there is some probability that there might be some eavesdropping on the channel. And if the QBR is less than the threshold, we proceed to the next step, that is the error correction. So in error correction, because during transmission and during detection, some error may happen. So in error correction, we mitigate, correct and mitigate those errors. But the issue is that during error correction, we need to exchange some classical information in the classical channel. So during this, there are some parity information to the classical channel. So some that any if or eavesdropper can gain some information about the secret key. So to compress that information available to if, we need to compress the final key, and we do this through privacy amplification. And once the privacy amplification done, we have the final secure key available at both Alice and Bob. So that are steps that we are currently performing in QKD, and we are doing this in our FPGAs. So this is the QKD solution that CDOT has developed. So here we have the Alice as the transmitter and Bob as a receiver. Currently, we are using DPS, that is differential phase shift and coherent one-way QKD protocols. This is our lab setup. And we have done some field trials also in the Indian Army network, and our QKD system is deployed with live traffic between the Office of Department of Telecom, Sanchar Bhavan in New Delhi, and the NIC headquarters in CGO complex. And this setup is running since February 23 without any interruption. And all the traffic between these two offices are encrypted by the keys generated by QKD. So as I told, to overcome the issue of dark fiber of quantum channel, we have also developed one solution that is called the multiplex QKD, where we are multiplexing the quantum channel, the classical channel, and 100G traffic in the same fiber. So in India, also in any other country, the dark fiber is very scarce, and cost of fiber laying fiber is also very high. So this multiplex QKD solution can be also is customizable. So it is preferable for greenfield deployments where there is no deployment done yet, but also it can be customized for brownfield application where there is also some fiber laid in the field, and we can modify those networks to have to update it to the quantum security using this multiplex solution. So we have one mux and demux entity in the transmitter side, that is in the Alice, and we have the opposite operation in the Bob side using the, and we are sending these three channels from Alice to Bob, that is the 100G traffic, the quantum channel, and the classical channel. And from Bob to Alice, we have two lambdas, two wavelengths. So one is called one is for the 100G traffic, and another is for the classical channel. So what are the applications? So QKD has this application in all the sectors that require strategic communication and requires utmost security. So first potential candidate is the data center communication, telecommunication networks. Defense is the most relevant area for QKD. Also banking, finance, and financial services and insurance sector, that BFSI that we called together. BFSI also has some applications for QKD, and some trials are also ongoing in BFSI all over the world. Blockchains can also use QKD. As I already told, the government built agencies are also using QKD for secure communication. And in India, that it is not of much popularity right now, but pharmaceutical and hospital industry also require some sensitive data to transfer between their local nodes. So there also QKD has some potential application. So this is a typical application, typical scenario of an existing network, where we have 4 sites. Like this can be of 4 different organization or same organization, like 4 offices. So we can have one internal network with VoIP, secure VPN, and other LANs, and they are connected over the IP network. To upgrade this with quantum security, you need to have 4 quantum nodes, that is the QKD node at each end. And we need to connect them through the QKD links, so they can be upgraded to quantum security. So I'm just finishing. There are last 2-3 slides. So what are so what are the future prospects in for QKD? Because currently what we are developing, like what CDOT is developing, it is in much sense it is a vendor proprietary solution, because the solution developed by one organization cannot be directly interoperable with another organization solution, because if I develop Alice, we also need to develop the Bob. But so the standards are not defined in such a way, so there is some loopholes are there. So such open areas we need to close, and there is some requirement of standardization to have interoperability, so that there is no chance of any market monopoly. So also to protect, as I told, there are in future MDI QKD is also getting popular, because some attacks have already been demonstrated in literature on the existing QKD systems. Also, currently our QKD system is around 100 to 150 kilometers. So there is one protocol called twin field QKD that overcomes this distance, and it can go up to 500 kilometers. So it will be very cost effective in that sense. And also some organization like Toshiba has come up with some chip-based QKD solution, where they are implementing the entire QKD protocol on a single photonic chip. And this is a very smaller size. And that will be the future of QKD, where we will have photonic chip-based QKD solutions. So currently as I told, the security of the data that is being transported over the network is under threat due to the rapid advancement in the quantum computing and the quantum algorithms, like the source algorithm and the Roberts algorithm that are already been discussed in this lecture. Also, the 5G deployment has started all over the world, and more numbers are getting connected to the network. And network security will be of highest priority than any time ever. So we need to have a foolproof security, and QKD is one of the solutions that provides the information theoretic security. Also, there are certain scope of development in terms of novel QKD algorithms, standardized solution to allow multi-vendor interoperability. In the recent days, Government of India has come up with National Quantum Mission in April 2023, where they have decided to spend around 6,000 crore over the next 8 years in 4 verticals of quantum technologies, that is quantum computing, quantum communication, quantum devices and quantum sensing. So CDOT is also taking a leading role in this quantum communication vertical under this National Quantum Mission. So thank you for listening, and I will be happy to answer any questions that you may have.
All right, thank you for sharing. There is a question for you, Dr. Arka Mukherjee. How could QKD work for blockchain?
Yeah, actually in blockchain, currently we are using asymmetric based cryptography. So that there are some literature have come where they have this asymmetric key is being replaced using this symmetric key, and the key for this symmetric encryption is being transmitted through QKD. If someone is interested, I can share that link to the literature where they have modified the blockchain network accordingly to get it operate with QKD.
Yeah, it was questioned by somebody who shared just now, which is Mr. Santanu. I'm pretty sure you'll get in touch.
Yeah, I'll share that literature to Dr. Santanu. They are actually basically modifying that encryption in from asymmetric to symmetric, and they are distributing the keys of QKD, symmetric key using the QKD.
All right. Thank you so much for your insightful sharing, Mr. Arka Mukherjee.
Thank you, ma'am.
Yeah, without further ado, we have our last sharing session today by Miss Tanya Sharma. She is currently doing her PhD. Her topic of research is quantum communication and information security. Miss Tanya, are you there?
Hello. Hello. Am I audible?
Can you hear me?
I can hear you.
I'll just give you a short intro before the floor belongs to you. She's been working in quantum optic laboratory in PRL Ahmedabad with weak coherent classes WCP and entangled photons, experimentally implemented BB84 protocols for 200 meters in field under DST project, currently analyzing the security threats to quantum key distribution and comparing the security proofs proposed to give a security and better key rate. She wants to model the device imperfection at both the source and detector end to defect any information leakage to the adversary and give a reasonable bound to secure key rates. This will ensure the security of QKD protocols. Without further ado, the floor would be yours. You have 20 minutes as per allocated. For the rest of the people who's listening, the attendance have been posted. You could take your attendance in the link that I'll share it in a bit. Thank you very much.
Thank you, Dr. Yukthamarani, and thank you, Dr. Krishnan, for the invitation. I'll be sharing my screen right now. I hope my screen is visible.
Yes, it is. Just put it on the full screen.
So I hope it's now visible on the full screen.
Yes, it is.
Okay, thank you. Thank you everyone for being here and listening to me. First of all, I would like to tell you that I'm working as a PhD student with Professor R.P. Singh, and as a researcher, I'm working on information security and quantum key distribution. Many talks before have talked about quantum key distribution, so I'll be briefing about the what and why. First of all, whenever we talk about a communication, there are two parties. One is the sender and one is the receiver. In QKD, we usually use the notation Alice for the sender and receiver for both. Now, when we are talking about this communication, two things are important. One is correctness and one is secrecy. Correctness means whatever you're sending should be going as it is to the receiver. And secrecy is that no other party except the authenticated users should have any access whatsoever of the information that is being transferred. But there'll always be someone who will try to listen to your conversations, and especially in defense and other applications where it is of the utmost importance that the communication has to be secure, it becomes an unwanted threat. Now, since the history, we have been using encryption as a technique to encrypt the texts, the plain text that we have using some key and an algorithm into a ciphertext. Then this ciphertext then goes to the receiver, who then decrypts. You using some sort of algorithm and some key that may be symmetric, anti-symmetric, as has already been explained by Dr. Arka, into the plain text, and then the decryption is done. Now, the problem is that the classical key distribution is secure up till now if you're using higher bit numbers, but due to the advent of technologies, various algorithms, and especially quantum computers come into play, this whole system of classical key distribution will fall into trap. Now, what can we do to overcome this kind of challenges in our systems, right? So we move to quantum key distribution. So the outline of talk would be, first of all, we'll discuss a little bit about the quantum key distribution. Then we'll move towards the protocols, for example, the BB84 protocol, decoy state, and CD protocols. Now, why do we need decoy and CD protocol? Was BB84 not enough? Because there has been studies that tell us that there still could be some attacks due to the implementation imperfections, such as PNS attack, to name one. Then I'll summarize the topic. So first of all, the main crucial thing here is the key distribution. Now, what is key? What is the key role of key is that whenever we are talking about communication and encryption, we ought to have one key using which we are encrypting it to the plain text. Now, how to distribute this key? So this key distribution is a central challenge in any quantum communication, in any communication, for instance. And then this key should be random bit of strings of a certain length. One main criteria should be it should not be guessable to any adversary, and any breach, if any breach is there, it should be detectable. Now, QKD does not say that, okay, if that QKD doesn't ensure that no attack would be there. What QKD ensures is that if there is some attack, then we will be able to detect that attack. If an adversary is trying to listen to our conversation, we will be able to detect that someone is trying to breach our system. How is QKD enabling us to do that? Now, any measurement on a quantum system perturbs that system. It changes, it perturbs, and it forces it to come to a state of the measurement state. So if such a thing happens, then we can know that, okay, some breach has been there. Now, what we are using here is our mutually unbiased basis. So if we are using two non-commuting operators, we could not precisely measure them simultaneously. Now, the third and the very important, I would say, the pillar of quantum key distribution is the no cloning theorem. That, for example, in classical communication, you can easily clone your system, but in quantum key distribution, it's very difficult. It's nearly impossible to clone your system. So the pillars of QKD are no cloning theorem, that if you have a state A, you cannot make 2 copies or more copies of that system. The second thing is that we are using mutually unbiased basis. For example, if you think in terms of light, we are using horizontal and vertical polarizations as one basis, and diagonal and anti-diagonal polarizations is another basis. Now, if we are sending our light in one polarization basis, then a measurement in the other polarization basis will give us a 50-50 chance of the right result. And if we are not able to measure, adversary would also have just this 50-50% chance of measurement. Third pillar is entanglement monogamy. So if we are going for the entanglement-based quantum key distribution, then between Alice and Bob, there will be distributed an entangled pair, and these 2 photons, for instance, will have no correlation with the third party. So coming to quantum key distribution, there are many protocols in quantum key distribution, and they are based on various strategies. One could be the discrete variable. That is, we are using discrete variables as our encoding systems. The qubits are discrete. Continuous variables, here we are using continuous parameters, for instance, phase or amplitude or Gaussian modulated QKD. In discrete variable also, we have 2 the categories. One is repair and measure, other would be the entanglement-based QKD. In continuous variable, we have once again prepare and measure. That could be the Gaussian modulated based and discrete modulation based QKD. And in continuous, once again, we have entanglement based QKD that is based on the squeeze states. Moving forward, this is just a brief overview of how vast this field is. Going step by step to just one category of this, to the discrete variable QKD, and one particular protocol that was the first protocol that was given in 1984 by Bennett and Broussard. Now, what they said is that if we are using two mutually unbiased bases to encode, let's say we are using polarization to encode our photons, then this is our channel, and these qubits are flowing through this channel from the sender to receiver. Now, these are our bits. Polarization states would be whatever we are sending in the two different bases. Then after this, we have here listed the basis choice, and the results would be whatever measurements we are making. Now, what do? We ask, Alice and Bob ask each other whether they have used the same basis or not. If they have used the same basis, they'll say, they'll keep that bit with themselves. If they have used different bases, incompatible bases, they'll discard those bits. So whatever we get from here is a sifted key. Also, since it has already been established in the previous presentation that after sifted key, there is error correction, there is privacy amplification. So here in this presentation, we are only focusing up till the sifted key. This is the BB84 experimental setup. Here we have used 4 lasers to combine and to make the 4 polarizations. These are combined together, and this is the launching optics that goes to our receiver. Then this receiver has some collecting optics because we are usually increasing the size of the beam to decrease the divergence. This is the collecting optics. And then this is the polarization state analysis, which is done by Bob using some electronics. And what we are using here are single photon detectors. These are avalanche photodiodes, and they are on-off detectors. So key here is, this is the source, that is the single, these are weak coherent pulses. I won't say single photon sources. These are weak coherent pulses. And whatever we are using here are single photon detectors, but they're actually on-off detectors. So this is just a picture to tell you that what have we done in PRL. So these are the 2 buildings where one is Alice, one is Bob. And this is another building where a reflector has been kept. So from transmitter, we transmit the beam, it goes to the reflector, it comes back to Bob, and the analysis has been done. So this we have done for 2 protocols, BB84 and BBM92. We have also recently performed decoy state protocol as well as CD protocol, which I'll discuss in the coming slides. Now, before going to that, what I need to mention here is that the physical implementation of the source channel detectors involve coherent weak laser pulses. These are not the single photon pulses. In case of entanglement, we have heralded single photon sources. The channel could be optical fiber or free space. Detectors could be the avalanche photodiodes, superconducting nanowires, or be it the single photon resolving detectors that are the upcoming things. So in theory, QKD is perfect. The source is perfect, no multi-photons are there, it's a single photon source. The channel is perfect, no loss is there. Detectors are perfect, 100% efficiency, and basis selection is perfect. The basis means the mutually unbiased basis. But when we go from theory to practice, what happens is that the source is no longer the single photon source, but is a weak coherent pulse, which has a Poissonian distribution. And when we talk about Poissonian distribution, there is, though very small, but still a probability of having multi-photons in that pulse. Though we said that there is no cloning theorem, but since that pulse itself is containing more number of photons, you yourself are creating 2 copies of the state. The channel is absorptive, and the detectors do not have 100% efficiencies. There will be dark counts, and the basis selection due to the minor misalignments is inevitable. Because the minor misalignment is inevitable, the basis selection is not that perfect. Moving on, the real question that arises here is QKD really secure in practice? Well, if I was Eve, what would be my quantum hacking techniques? I would like to gain the reasonable amount of information without alerting Alice and Bob. The first thing, because QKD, what it does is that if anyone is trying to breach, it will tell us that any breach is there. What if Eve is smart enough to bypass that thing? And Alice and Bob have no clue whatsoever that Eve has been trying to listen to their conversation. But classical was easy, but in quantum, there are basic pillars, the mutually unbiased basis, no cloning theorem. So what I need to do is I need to find the loopholes. So the question is how close I am to the practical QKD, how close the practical QKD is to the ideal protocols. And if there are some deviations, theory to practice deviations, how can those be exploited? So there have been many attacks listed in literature. These are very few that I've mentioned here. One being the photon number splitting attack, fake state attack, time shift, and so on. But due to the lack of time, I'll be discussing just one of them, that is the photon number splitting attack. What happens, as I mentioned, since we are using weak coherent pulses, these weak coherent pulses have very small, but they have some probability of having multi-photons in a pulse. Now, since there is this small probability, this multi-photon signal could be split by Eve. So what does Eve does is it sends some part of the signal to Bob and keeps the other part to itself. Now, since there is no breach in the system and we cannot find it in Kubler, how are we going to address this problem? So the signature of this attack is multi-photons are much more likely to reach Bob than the single photons. What do? We go to the decoy state protocol. Now, this is an addition to the BB84 protocol mentioned by Bennett and Bansal in 1984. What this decoy state does is that along with the signal, it also adds some decoy pulses. Now these decoy pulses have the mean photon number different from that of the signal pulses. Alice randomly sends signal as well as decoy to Bob. Bob records the measurements. Then Alice publicly announces the signal in the decoy states. What are the signal? What are the decoy? But initially, before, when the quantum communication was going on, when the key distribution process was carried on, neither Bob nor Eve had any information that which are signal and which are decoy. Bob then computes the transmission probability of signal and decoy. And if this yi is the yield, and yield is just dependent on how many number of photons are there in that single pulse. Now, this single pulse may have 1 photon, 2 photon, 3 photon, and so on till infinity with different probabilities that is governed by the Poissonian statistics. Okay. Yeah. So, if what do Alice and Bob do? They find this yield, that is the conditional probability that, okay, this pulse had I number of photons, then what is the yield of this pulse? After calculating this, they find it for both the decoy state and the signal state. If these two yields are different, then they say that the attack has been there, and then they discard that protocol and they once again carry on with the key distribution process. But if it is not the case, then they carry on with the sifting, quantum bit error rate estimation, error correction, and privacy amplification. So one more protocol to it is the coincidence detection protocol. So what happens in coincidence detection protocol is that the setup is exactly same as BB84. Here we are not adding any additional pulses with the signal. But what we are doing here is we are recording the coincidences. We had 4 detectors. Now in these 4 detectors, we see that, okay, how many times 2 detectors had a simultaneous click? Then
Tanya, your last 5 minutes, yeah?
Sure. I'll wrap it up. So then we find that, okay, 3-fold coincidences. How many times the 3 detectors simultaneously clicked? Now these 2-fold and 3-fold coincidences are dependent on the mean photon number. Now, if the coincidences fall below the threshold value, that is the estimated value, they abort the protocol. This adds an extra layer to overcome the PNS attack, because if a PNS attack is there, the mean photon number would be altered. And if it is altered, we get some coincidences that were not expected. So we are able to detect that, okay, a photon number splitting attack has been here. This enhances the key rates as 2 and 3 full coincidences also contribute to the key generation. Because initially in VB84, we were discarding any coincidences. But here, since we are using them as a flag to find PNS attack, what we do here is we also include them in the key rate. So it enhances our key rate. To summarize this, what we have discussed so far is that quantum key distribution over classical key distribution ensures information theoretic security. Theory is very important because this information theoretic security has been established in theory, but when we go to the practical implementation, which has some device imperfections, adversary might exploit those device imperfections to gain some information out of our system. Attacks are possible. For instance, we discussed the PNS attack, decoy state and coincidence detection protocols, and many more also help us to overcome this PNS attack. The security certification. In the end, I would like to conclude that the security certification is most important. Now, what is security certification? We need to reduce the assumptions that are there in the security proofs. Many security proofs have been given to QKD. We need to reduce those assumptions. We need to characterize our devices properly so that at least for our QKD systems, we know that what are the limitations of our devices, or how those device imperfections could be exploited by an adversary. What could be the information leakage, improvement of devices or the protocols. So either way, one is to improve our devices. For example, from weak current pulses, we could go to single photon sources. From on-off detectors, we could go to photon resolving detectors. Other ways to improve our protocols. For instance, decoy state and detection, coincidence detection is a better way than the BVD protocol. Similarly, as mentioned by Mr. Arka, that MDI QKD, measurement device independent QKD, are a better way to remove these device imperfections altogether. So with that, I would like to conclude my talk and thank you all for listening to me. This is my group, and I'm thankful for Professor R.P. Singh for giving me this opportunity to research in this amazing topic. Thank you, everyone.
Thank you, Ms. Tanya. So if there's any question for Ms. Tanya, feel free to ask. I think I would like to wish you all the very best in completing your postgraduate studies. So in line with that, we had 6 speakers today, and I hope all of you attended here would have heard an insight about quantum communication. It's a very new field to me myself. I'm from an HR expert. So what I heard today, the importance of data transmission, the importance of security, a lot of theories has been exposed and shared. And moving forward, I think these are the things that will be taking place in our life very much soon with technology interference, how things are being transmitted from one end to another end. So quantum communication would be the way forward, I think, in many perspectives. So with due respect, thank you to Dr. Umar to allowing me to chair this session with 6 profound speakers today. So thank you so much once again, and I wish you a pleasant evening on your side. Thank you, everybody.
Thank you, ma'am. Thank you very much. We are closing the session. Thank you.